Radiator here is where we're transferring the heat. Now, remember, this is not an artist, okay? But anyways, our radiator is the point where we're transferring our heat out of the liquid and into the air. Our water comes up into comes up through the lower radiator hose into our water pump, goes through our engine block, and then we'll have an upwards travel throughout the engine and come back to our valve that we're calling our thermostat. And we hear a lot of folks that think that problem where an engine that only overheats under heavy load, it's got to be the thermostat or it's got to be the fan. There's really no variables there. If you've got a problem with the thermostat, you're going to have overheating issues or temperature issues, irregardless of the load. The load does not affect how that thermostat, I can't spell, can I? The thermostat functions. If you've got thermostat issues, it doesn't know whether you got 80,000 pounds behind this truck going up a hill or it's sitting in the yard idling. You'll have the same kind of problems. If it's the water pump's only job is to circulate that water. And rarely do we have failure to circulate issues with water pumps. 99% of water pumps get replaced because they leak, and the bearings and seals in the shaft are shot and they leak. But it is possible, I've seen it twice ever, have impeller problems. But there again, you'll have just troubles with water circulation, and honestly, in the cases where you have trouble with the water pump impeller, usually, well, I guess there again, small sample, I've only seen it twice ever. Both of those vehicles came in the shop with the complaint that the heater didn't work. Because the induction of drawing cool water in here and letting the hot water go up seemed to be circulating it enough that there wasn't much of an overheating issue, but because the water pump wasn't pushing that water, you didn't get water flowing up through, because there again, at this point, right about here, we're going to take hot water into the passenger compartment and run it through a little radiator, and that's where we're going to get our heat that we put in the cab. And then we'll take this hose and we actually dump it back in down here once we've taken the heat we want out of it. But anyways, without the water pump pushing, it doesn't push hot water up there. And one of those was one of the freight liners that hauled beets to the sugar factory. And the impeller had completely come off the shaft. But it came, and so it was hauling 126,000 pounds and surprisingly wasn't really overheating. It came in the shop because the heater in the cab didn't work. And then again, like we had talked about last week, the fan, and therefore the clutch that turns the fan on when needed, the fan's only needed when we've got low airspeed coming in through the radiator. But what we see a lot, and like I said, multiple times a week, especially in the summer, is where the air passages coming into this radiator are partially blocked with cheap grass and bugs and dirt and trash, and you can't get quite enough airflow through it, so we're not getting enough heat transfer here. And in some of those cases, the liquid tubes that are coming through the radiator are plugged up with mineral and not circulating the water right. But in that case, the point is we're not being able to transfer enough of the heat out of the liquid into the air. So our problem is right here at the radiator. And 99% of those phone calls we get with that symptom, we will remove enough stuff that we can take air and blow in the reverse direction that the air normally flows, and blow a bunch of the cheap grass and wheat chaff and dirt and bugs, because the airflow's been packing them in from this side. We take an air hose and blow them back out, and then we sweep up 2 shovels full of trash off the floor, and it's fixed. But it can be a liquid tube blockage, but at any rate, that problem we're describing right there is a failure to transfer enough heat at the radiator. Any questions about anything on last week's quiz before I move on?
So when you see trucks with a piece of cardboard in front of the radiator because you can't get warm enough, what's the issue there?
Typically, it's either the thermostat is not closing correctly, or in many cases, it'll be a bypass. Because most engines will actually have a small bypass that bypasses the thermostat and comes back into the top of or into the water pump at some point and circulates that water. But in that case, you'll typically see that in the winter when we're actually transferring the heat out of the engine faster than we want. And instead of fixing the problem, well, we'll cardboard it up and get by. But I would say in at least 50% of those cases, the thermostat being not closing completely is the problem. And in some cases, we run into this where last summer, the guy put a real cold thermostat in it because he was having overheat issues. And now, well, it's opening awfully prematurely and not building enough heat this winter. And I guess since we're talking about thermostats, an engine, all of our automotive truck engines that are running on gasoline and diesel fuel, that combustion process happens most efficiently if we have somewhere in that 185 plus degrees of temperature on that top of that cylinder head. So you'll notice the vast majority of factory thermostats are set to open here whenever the water temperature is around 192 degrees. And that's really a good temperature to run. And a lot of times when fellas are having overheating problems, that most often are radiator and or air circulation issues, they try and mask the problem by putting a 160 degree thermostat in them, and it doesn't totally fix the overheating, and it creates other problems. And then they notice the fuel economy went down a little bit too. The fuel will atomize from liquid into vapor better if we have that temperature up over 185 degrees. And therefore it'll burn better and you'll get more power out of it instead of just wasting it. So you have better fuel efficiency if you leave the factory temperature thermostat in there and fix the overheating problem instead of trying to fake it by putting a cold thermostat in there. So the subjects on the schedule for tonight are induction, exhaust, and emission controls. So we'll start with induction, and induction is just talking about how we're getting our air into our cylinders, is all that's big fancy word means. And I guess I'd like to start that discussion talking about air filters. As you can imagine, when we're running precision machined parts, if we throw a piece of dirt in between them and rub that dirt in between them, you can take a piston that the skirt looks like that and make it look like that, and you know, tear up some really nice parts and create a lot of problems. Whenever you throw dirt in between that cylinder wall and the piston, typically it'll grind the cylinder wall in, the piston, but the thing that'll suffer the most is these sealing rings, and you'll have a loss of compression. So you'll wind up losing some of the compression we wanted on top of the piston past those rings, as well as you'll flow oil going the other way. And it'll be one of those engines that uses a lot of oil. I would say at least 25% of the engines I've been paid to replace in my life have been caused by people doing dumb stuff with air filters. And so just thought I'd throw that out there. One of the best things you can do for your engines is keep that air filter in good shape, change it when it needs changed. Just a little bit of a side note, but blowing them out with an air hose isn't necessarily the best idea. I've seen several engines destroyed by that. What can happen, not necessarily will happen, but if you take an air hose and blow it out, you can tear that paper element if you're not kind of careful. And then that tear in the paper element lets the dirt through. So don't really recommend blowing them out with air. Now, a lot of air filters, you can get a lot more miles out of them if you'll thump them out. We see a lot of guys thump them against the tire, and you can get a lot of dirt out of them and use them some more, but you tend not to run the risk of tearing the paper so much. And you can do it carefully with an air hose and probably get by, but I've seen more than one engine that was destroyed because the fellow was a little too rambunctious with the air hose and tore the paper element, and then the dirty air came through the tear and wrecked the engine. But we want to feed the engine clean air, so typically where we'll start the induction is air will come through an air filter, and then it usually will come through some form of tubing to get into our cylinders. On our multiple cylinder engines, like all of our automotive ones are, we'll have some type of an intake manifold, which just is a big fancy word for, hey, we're going to have one place the air comes in and we're going to feed it into all our cylinders. And those intake manifolds can get pretty complex. Sometimes I wonder if the boys in Detroit just didn't have anything better to do today than make something squirrely looking, because some of them, not sure if there's really a purpose for. Just for fun, I brought in a squirrely looking one. This one's actually off of a Triton Series Ford V8 gas engine. You can see this is the place where there's a hose coming from the air filter, comes through this throttle body, and the air travels down, and it goes down through the middle of it into this plenum here, they call it. And then each cylinder has a runner coming out of it. You can kind of see them coming over this way. They come over like this. And here's the ports going to the individual cylinders. There are some of them these days that are even more complex than that. And their excuse for that is trying to make the airflow even to all 8 cylinders and to make it flow with not a lot of turbulence, so that, well, and in some cases they want to control the way that air swirls going into the cylinder and make it the same in every cylinder is what they're attempting to do there. So there's 3 kinds of induction we want to talk about. So we're going to talk about what we just looked at there. I'm good at grabbing dead ones. So what we looked at there is an engine that we would call naturally aspirated. So that's a big fancy word for saying it's got to suck its own air. So there again, our cylinder, we've been talking about this whole time, as that piston travels down with our intake valve open, it has to suck its own air. And another scientific type sounding word for suction is vacuum. Well, vacuum is a term for air pressure that is less than atmospheric. But anyways, a naturally aspirated engine sucks its own air in. We're going to have two types of what we're going to call forced induction. And as you could guess from that term, forced induction versus naturally aspirated, we're forcing the air into it and instead of just naturally letting the piston suck its air in. The two common types of forced induction are turbochargers and superchargers. Now you can imagine some of those names had to come from the marketing department, right? 'Cause they sound really cool. So why would we want to force air into the engine instead of just letting the engine suck its own air in? Any thoughts on that? Why would we want to jam more air in there?
More compression, power.
Yeah, both of those are true. And the way we're getting more compression and more power, well, what we're after in all of that is getting back up to our whole thing about hydrocarbons and oxygen, those two combining to make our combustion. We want more oxygen molecules in that cylinder is what we're after. The more oxygen molecules we have in that cylinder, the more fuel we can put with it, and the bigger our detonation or our combustion will be, and the more power we'll make, like Rich said. So that's what we're up to, is we're wanting more oxygen to work with. So our turbocharger, and basically these two are just different ways of driving that. But both of those are taking some form of a fan, more or less, and blowing air into our engine. The turbocharger is exhaust driven, by definition. And the supercharger is mechanically driven. So our turbocharger, we're doing something like this. We're taking a fan blade. I don't know if I can draw a fan blade on its edge very well, but you have to work with me on that a little bit, okay? We're taking a fan blade and we're attaching it to a shaft, and we're going to support this shaft with some bearings so it stays put. And of course those bearings need to be lubricated, so we're going to have some seals, and but the point is the other end of this shaft has another fan blade on it. So what we're going to do here, we're going to blow our exhaust on this fan blade. It's going to turn the shaft. The shaft is going to turn this other fan blade. And this fan blade is going to compress the air and push this is our incoming air. Intake, you're right. Here, we'll use that word instead. Joe, I like that. Because it's our intake air that we're intaking into our engine. So that's basically all a turbocharger is. On a supercharger, we're just going to have a fan blade, more or less, and we're going to drive it with either belts or chains or gears. So we're going to take actual rotational energy from the crankshaft in one way or the other and turn a fan blade and blow air into the engine mechanically. This one there's different ways to control it a little bit, but more or less this fan blade is, the speed of it is going to be directly proportional to the speed of the other shafts in our engine. This one, there's games they play with how they control the pressure against this wheel, and therefore it can control how fast this one turns. So I brought with me tonight a turbocharger that I've partially disassembled. So you can see on this one, the exhaust comes in through these ports. It swirls in this chamber and turns that fan blade you can see there. So that fan blade on that end turns the shaft that comes through it, and that turns the compressor wheel on this end. So this compressor wheel normally sits in this housing, and our incoming air comes into the middle of it, and then that fan blade blows it and it comes out through here. So this one is pretty typical in that it's designed at peak output to make the air coming out of here headed towards our engine somewhere in the ballpark of 25 psi. Well, you can imagine air at 25 psi compared to atmospheric air. We've already pre-compressed it some, and a given volume of that air has a lot more oxygen molecules in it than at atmospheric pressure. There's pros and cons to both of these systems. The biggest two cons to a turbocharger, the first one being heat. Since we're using exhaust to run this turbocharger gets pretty hot, and some of that heat transfers into the air going through it. Well, that's counterproductive, because when we talk about air density, cooler air is more dense than hotter air, right? That's why the hot air balloons fly, right, Joe? We heat that air up and it expands and they can fly. Well, so we've pressurized it, but we've heated it. So the pressurizing of it, we can do a lot more pressurizing than the loss we get from the heating expansion. But to counteract that, in many cases, I guess I'm going to make some more room to work here. And in many cases, vehicles with turbochargers will run what's known as intercoolers or aftercoolers or charge air coolers. But at any rate, they're all designed to take that air that we've compressed going through the turbocharger, but we accidentally heated it up, and cool it back off. Because what we're wanting to do is put as dense of air as possible into that cylinder so we get as much oxygen as possible in there. So in many cases, our configuration will look something like this. We'll have an air filter. We'll have a hose from that coming into the center of our compressor housing of our turbo. Then the air coming out of this compressor housing will come up front, and usually this intercooler, if it's an air one, which most of them are anymore, will set out actually in front of the radiator. So it'll look just like a radiator. It'll actually have the same kind of fins and the same kind of tubes, but what's flowing through it is the air we've compressed in this turbo. So we've taken the dirt out of it with an air filter, we've run it through the turbocharger to compress it, but we accidentally heated it up. So our radiator would sit like this. So I'm kind of drawing a view from above. if that makes any sense. So this would be like the top of our engine. Then this air coming out of this side of our charge air cooler is compressed and cool. And then we'll take this and plumb it to our intake manifold. So we're pushing that in. So at this point, our air we're saying is cool, but it's not compressed. After we've gone through the turbocharger, we've compressed it, but it's hot. So putting it through, now there are some engines that instead of this being a heat exchanger that exchanges with air coming through our grill, they run antifreeze through it, and so that would be a air to water type charge air cooler. Those are not very common anymore. They were found to be not as efficient as the air-to-air charge air coolers. But a lot of vehicles, when we first started playing with turbos, and I say playing with, the manufacturers started using some of them. They really hadn't built chassis that had enough room to put a second radiator in front of the existing radiator. And so they played with the ones that used antifreeze in them, that instead of putting this out in front of the radiator, mostly for space constraints. Because as you can imagine, if we're taking this and we're running it through something that has 70-degree air to exchange heat with versus 190-degree water to exchange heat with, yeah, the 70-degree air is probably a better way to try and get rid of more heat. Make sense? So, got a couple little videos that are probably going to help visualize this a little bit better than my crude art. Let's see if we can. Not sure that's slow to come on, but that seems a little extra slow.
I see a green dot.
You do?
Yeah, it's blinking.
Okay. Well, maybe that's a good sign, though.
No, quit blinking. Oh, wait, there it is again. No?
Yeah,
Oh, yeah.
I think it's starting to come
Yeah,
alive.
almost catchy. Yeah, I see it. Almost.
Almost. Would somebody catch that farthest north light switch? I think it'll make the screen a little easier to see.
Some more?
I think that'll work. What do y'all think? Okay.
Yeah.
A turbocharger is nothing but a centrifugal compressor. The principle here is forced induction. It's the process of forcing compressed air into the intake for combustion. First, we will see the basic parts of a turbocharger. A turbocharger consists of a compressor housing, compressor wheel, turbine housing, connecting shaft, bearings, and oil seals. The middle part held together is called a cartridge. The compressor wheel and the turbine wheel are connected with shaft, so that turning the turbine wheel will turn the compressor wheel. A turbocharger is designed to rotate over 100,000 RPM. An oil feed line from the engine will lubricate the shaft and the bearings, providing less friction. Now, let's see how the turbocharger works with the engine. An engine without any forced induction device is a naturally aspirated engine. The air is pulled in through an air filter by the suction force of the piston. Then it gets mixed with the fuel, compressed, and gets ignited. With the turbocharger introduced, the exhaust gas from combustion turns the turbine wheel. This turns the compressor wheel, and more air is compressed and fed to the engine. Let's take a closer look. The exhaust gas from the engine will push the turbine wheel, and this turns the compressor wheel, forcing more air into the engine. According to gas laws, for a constant volume, increasing the air pressure will increase its temperature, so there will be a difference in temperature after charging. Forcing this air into the engine can reduce efficiency and cause knocking. In order to cool this air, an intercooler is introduced. An intercooler is an air-to-air heat exchanger device, which helps to cool this air before it enters the engine. So introducing an intercooler into the system will increase the charge density by cooling the air and provides volumetric efficiency. In conclusion, a turbocharger will provide more air to expand on combustion and produces more power. And that's how a turbocharger works. Thanks for watching, and
Well, are you glad I don't talk like that, fella? So this next little video I've got for us to watch, it's talking about superchargers, which, like we'd said, are the mechanically driven ones. A couple of things that were mentioned in that last video that wanted to touch on again is, if you notice, they said that the turbochargers were designed to turn 100,000 RPMs. Well, I'm not sure if that's true of all of them, but they turn an incredible speed. In the engines that I'm familiar with, they typically turn between 10 and 20 times as many RPMs as the crankshaft. For example, in one case that I know of, when the engine's turning 3,000 RPMs, the turbocharger shaft is typically running about 45,000 RPMs. So you can imagine spinning that fast, those bearings that are supporting that shaft need to be well lubricated. And there's not a lot of mass there, and they are really good quality bearings, but they do need to be lubricated. So that's why in most owner's manuals of turbocharged vehicles, engines, equipment, it'll talk about a cool down or a spool down. So think about if that shaft is turning 30, 40,000 RPMs and we suddenly cut the oil supply to it. That's not going to be a great thing. Well, if you're under power and you are done and you suddenly shut the engine off, that's in effect what you've done. Because that turbocharger, as you can imagine, when it's turning that kind of RPMs, it takes a little bit when you let the engine come back to idle for it to spool down. And even at idle, when you're idling at 700 or 800 RPMs, typically in that case, the turbocharger is still turning almost double of what the crankshaft is. But anyways, that's why in a lot of those owner's manuals, you'll see when the engine's been under load, let it idle for at least 30 seconds. Some of them will have different times, but a lot of them in the pretty modern stuff made in the last 15 years at least, or more, will say you need 30 seconds of idle time before you shut the engine off. That does not have to mean that the tires aren't turning, because there again, it's not uncommon if you're coming up to the house, your engine may be at idle while you're coming that last few hundred yards up to the house or whatever. But anyways, you don't want to just shut an engine off suddenly after having it wound up. Is that a turbocharger takes a little while to spool down, and when you shut your engine off, remember we talked about the whole lubricating system? When you shut the engine off, that oil pump, which is pumping oil to all of that and pumping oil to the bearings in that turbo, you're shutting that off. So if you give a little bit of time for the RPMs of that turbo to come down before we shut the oil supply off, because when you shut the engine off, it's not uncommon for, even if it's just idling, it'll take a good 10 or 15 seconds before that turbo stops spinning. If it's really wound up, it can spin for 2 or 3 minutes. Well, spinning for 2 or 3 minutes after you cut the oil supply to it, that's a good way to wreck it. Any other thoughts or questions about turbos real quick before we watch this one about superchargers?
So the turbo runs once you start the engine?
Yeah.
So what happens at a couple thousand RPM when you hear some funny things going on?
When you hear that whine,
yeah,
it's ramping the speed of it up, because as the drive pressure, and drive pressure is talked about when you're looking at turbocharger design, but it's the difference between the pressure between the engine cylinder head and this wheel, and the pressure between that wheel and the tailpipe. So that difference in pressures is what runs that wheel. Well, as you start throttling on it, and you've got a lot more exhaust gas coming out of the cylinder head, you'll ramp that speed up exponentially. And at that point, you know, as you're accelerating, that's when that shaft, instead of going 2 or 3 times the speed of the crankshaft, it'll go to doing 15 or 20 times the speed of the crankshaft. And as that accelerates up, what you're actually hearing in most cases is the compressor wheel. You're hearing the noise it makes as it starts pushing more air. That's actually what you're hearing, is the way it comes through this chamber right here. It'll come in here and get turned there. When you hear that whining noise as they spool up, that's what's doing it.
It feels like quite a bit more power at that point too.
And there again, it's not a straight ratio. It, like I said, ramps up exponentially as the drive pressure goes up. We'll talk about one more thing that helps control that here. Well, maybe now's a good time. You might just turn the lights back on for just a second. So there's a lot of design work that goes into these turbos as far as designing the size of the chambers, the size of the wheels, and the angle of the pitch on those blades. And one of the big things they talk about in turbo design is AR, aspect ratio, and it talks about basically how much air volume this wheel moves compared to that one, and it is a ratio. Because, well, there's 2-year degreed classes on turbochargers alone, so we won't get into all that, but this wheel here, in general, the smaller it is, the quicker they will spool up. And spool up is a term used for, you know, how fast the shafts are spinning. But anyways, the smaller this chamber is, because you shove a given volume of air through a small chamber, it's got to go faster. As it goes faster, it makes that wheel go faster. So if this chamber is smaller, they'll spool up quicker. So from the time you press on the throttle until you have that power surge you feel will be a shorter time. But if you get that too small, then when you're on the opposite end and you're your foot's clear on the floor and it's been there for 5 minutes, you can have that shaft so overspooled that it's going 150,000 RPMs and it flies apart. On the opposite end of that, as you make this larger, the slower that will come up to speed, but the longer it can sustain it. Well, there's basically 2 ways that they try and hit a happy medium with that. And this one runs the most common one, which is known as a wastegate. So you can see this gate here. Well, the exhaust coming out of the engine up into this, normally when this is shut, all of it has to go through that wheel. But if it gets up to the, in this case of this turbocharger, right about 24 PSI, when there's 24 PSI in this tube, which is the tube going to our intake, it puts that pressure out through this into this diaphragm chamber, and it will push on this rod. And when it pushes on that rod, there's a big spring that normally holds this shut. When it pushes on that rod and opens this, we're letting some of our drive pressure that was going in there that normally turns that wheel escape through here instead. So by using this wastegate system, they can keep this small so that it spools up rapidly, but then when it gets to the point where we're fixing to overpressure or overspool it, well, we can just open this and reduce that drive pressure so that we don't kill it. And that's the most common system used, and it's very inexpensive. A lot of the engines made in the last 10 years are using a much more complex and expensive design. And what they're doing on this exhaust turbine wheel, they're making it where they can change the pitch of those blades. They're using a lot of the same mechanisms that changes the pitch of the blades on the helicopter rotors, and they're putting it in there so that at different speeds and different desired pressures, they can change the pitch of that blade and change how fast it turns the shaft and how much pressure it creates on the compressor side. As you can imagine, this, which is known as a fixed turbo with a wastegate, but a fixed turbo, especially if you ignore the wastegate, but it's going to be most efficient at a certain RPM and a certain drive pressure. What's known as variable geometry turbos, they abbreviate that VGT, but the variable geometry turbos where they can change the pitch of the blades on this exhaust wheel, they can change that so it spools up real fast, but it doesn't overspool at the high RPMs, and they can make it really efficient at the whole range of engine operating conditions. 2 drawbacks to that. One being it's incredibly expensive to manufacture to begin with, and it has to be tied into the whole computer engine management system. The other thing about it is the failure rate of them is very high. You put that complex of a mechanism in the exhaust flow where you've got black carbon and soot, and it fouls things up. Well, it fouls those blades up and creates problems. In a much shorter time span than this style of turbo will ever have a problem. So, I hate to say it, but it's not uncommon for us to see those variable geometry turbos fail and get replaced under warranty by 50,000 miles. And it's not uncommon for one of these fixed geometry turbos to make it 200,000 miles. So pros and cons both ways there. The other con to turbos in general is that in general, our engine is most efficient if it can breathe well on the exhaust side, so that when that exhaust comes out of the exhaust valve in our cylinder head of our engine. We let it flow freely out to the atmosphere, because that lets the whole cycle of air coming in on the next stroke, because there again we're exhausting, and if we can get as much of that exhaust out of the cylinder as possible, then on our exhaust stroke, then on our next stroke, our intake, we can get more fresh air into the cylinder. So the more freely we let the exhaust flow, the better engines perform in general. We're restricting the exhaust with this. So we lose some efficiency in that way. But the advantage of the compressed air on the other side does far outweigh the loss because of the restriction in the exhaust flow. Okay, what do you say we watch this video about superchargers now?
Roots blower rotors are available in different designs. They can be equipped with twisted lobes, for example. But they also come with straight lobes. First, we look at a very simple variant with straight lobes. The housing has 2 inlet ports and 1 exhaust port. The rotors have 3 straight lobes and do not touch each other. A gear wheel transmits the rotational motion. To better understand the airflow, we simply pass a colored liquid through the blower. This allows us to easily understand how the lobes convey the fluid from the suction side to the...
So I wanted to point out that the incoming fluid, which what we're working with is air, comes in here where this cavity between the lobe is open. And when they come around here where these lobes, the opposing lobe is displacing the volume in between the other rotor's lobe, it presses the fluid out. Now this illustration has the blower upside down to what they typically are in all of the applications I've seen. Because typically you'll put this on top of your engine and the compressed outflow will be being pushed down into the engine. But they, here in a minute in this video, flip it upside down. So don't let that confuse you, that it, at the moment it is upside down to what you'll typically see on
the pressure side. Roots blowers used in cars usually have rotors with twisted lobes to ensure low vibration and quiet operation. Touching rotors are also not desirable here because the resulting heat would cause the supercharger to fail due to seizure or jamming.
So you'll see very few superchargers, and you'll see a lot of turbochargers by comparison. And it seems like the output from the turbochargers is easier to control. We talked about some of the different ways it can be varied. And of course, this is not easily varied for different RPM and load requirements. So you won't see a lot of superchargers out there. You know, there's a few of them, but in factory built engines in both on-highway vehicles and off-highway equipment, there are some. The place we saw the most of them was in the old 2-stroke Detroits. And they had to have them to push the air into them. But, you know, there's been a few cases where Detroit, as far as like Ford, GM, and Chevy have built a few things with superchargers, but not very many. Any questions about superchargers before we move on? All right. Can we have some light again, please? Thanks for helping with the lights there.
So if a turbocharger fails, what's the most common reason?
Poor lubrication in most cases, or the control system failing and it overspeeding. There can be some issues with bearings as well. For example, this is a turbo that's designed to run around 24, 25 PSI. And it's controlled by this wastegate actuator. Well, you can see it's adjustable. Well, some of the kids that wind up with these and want to make them go faster, they'll turn this rod all the way up. And this thing will come uncorked at about 55 PSI and just scatter like a grenade. And okay, in the middle there, if you turn it up to 35, where is its maximum, they'll last fairly well, but they're not going to last nearly as long as they did because we're putting more strain on the bearings in this center cartridge than they were really designed to work with. But the majority of the turbochargers we replace, we're replacing for bearing failure. So the shaft is no longer staying centered and it flops bad. This is actually one we replaced. Normally this compressor housing is not nearly that black and yucky. Because this is coming in through this tube is air that just came from the air filter and we're just compressing it. So it shouldn't be that dirty of a process. I mean, it's not perfect, but this turbo was passing lots of oil. So there was a lot of engine oil winding up coming past the seal plate and into this compressor housing. And actually when we replaced this turbo, we took the intercooler and drained about 2 quarts of oil out of the intercooler.
I just had one go out on my tractor. The seals went out and man, did it blow oil.
And this is pretty rare, but there is an extreme case where that seal blows out so bad that there's enough oil coming into this airflow that the diesel engines will run on that oil. And it's just like you rip the throttle wide open, you know, mash the pedal to the floor, and it'll run like that till it runs out of oil. Well, you can imagine if an engine that was designed to redline at 3,000 RPMs, it's at 5,000 RPMs when it runs out of oil. It's a catastrophic failure. There are getting to be more and more turbos all the time that will also be water cooled. So they'll have a passage coming through here and they'll run a small hose of coolant, you know, antifreeze over here to help cool this center section. This one is not, and this one is normally installed in this orientation, and we'll have coming from the oil filter housing, there's a port on it, so there's pressurized engine oil coming in here, and it's lubricating those bearings, and then the excess comes out this drain port here and comes down a pipe that just returns to the oil pan. And like I said, the newer variable geometry turbos, normally they get replaced because the variable pitch vanes are jammed up with carbon and won't adjust. So the vast majority of diesel pickups have run variable geometry turbos for about 10 years now. And they work really nice in a broad range of conditions, but they don't last as well as we'd like them to. So back to the subject of exhaust. Exhaust is kind of like we talked about the first week, it's taking out the trash. we've used the power out of this and we want to get rid of it. And under most conditions, the more of it we can get out of the cylinder during our exhaust stroke, the more room we've left for fresh air during our intake stroke. But exhaust is a fairly uncomplicated thing until we start looking at emissions controls, which but anyways, you know, the most basic of exhaust is just going to be a pipe coming off of the cylinder head, but typically that's pretty loud. So a lot of times we'd like to be able to hear the radio, and so we'll typically run a muffler. And a muffler is just designed to try and dampen some of those shock waves in the pulses of exhaust. Because I guess what I wanted you to think about just a little bit is, a lot of folks don't realize it, but the exhaust coming out the tailpipe is not a steady stream. It's pulsing. Every time you have an exhaust valve open, you get a pulse of exhaust, and then when that exhaust valve closes, well, that pulse is over. And then when the next exhaust valve opens, you have another pulse, which is another push of that combustion gas. So the more quiet you want a muffler, the more you want to dampen those pulses. So a lot of our mufflers that are factory automotive mufflers are going to look a little bit like this. Our pipe coming from our engine is going to come in this end and go all the way to this end and dead end down here. And we're going to have a bunch of little bitty holes in the sides of it all the way down. We're going to have another pipe, which was dead ended here, and it's going to come out through this end. And we got a bunch of little bitty holes there. And in between the two of them, we're typically going to have some kind of a fibrous material. A lot of them, it's actually a ceramic wool. It's a wool made from ceramics, which will withstand a lot of heat. But as you can imagine, that style of muffler is going to be very quiet, but it's going to restrict the flow enough that it will adversely affect performance some. So you'll hear the term straight through muffler. What will happen with straight through mufflers is, as the term implies, the pipe will go straight through, and what you'll typically have is they'll actually perforate the pipe and chop it so that it has some protrusions that stick down into the flow to divert up, and you'll have that some kind of fibrous material in here. So as those pulses of exhaust come down the pipe, some of it will be diverted out into these passages, and it'll wind up coming down through here and coming back out later. And these protrusions sticking out into the pipe, the larger they are, well, the more sound they dampen and the more they inhibit the flow. So it's somewhat a trade-off where you pick one that flows enough that you get good efficiency out of trying to get the exhaust out of the cylinder during the exhaust stroke, but pick one that isn't so noisy you can't hear the radio. Now the muffler design changed a lot. Oh shucks, I meant to bring a catalytic converter with me tonight and I forgot. But most all of our engines are going to run some emissions, what's known as after treatment, which are devices designed to try and control how much emissions we're putting out the tailpipe. Now, I'll say that the biggest advancement in tailpipe emissions over the last 30 years has by far been just fine-tuning the air-fuel mixture. Because the better the fuel injection systems get and the more balanced that is, with none of the quote-unquote emissions control devices that are designed just for emissions controls, the engines built currently produce like 5% of the tailpipe emissions that common engines did 50 years ago. And there again, it's helped our fuel economy too by just getting that air-fuel mixture really right. But as tailpipe emissions requirements from the federal government get tighter and tighter, in order to sell the vehicles in our country, the manufacturers have to make it even better. So there's one of the common after-treatment devices is known as a catalytic converter, and we talked about those just a little bit once before. Catalytic converter. And what these typically are is they'll, at a glance, be a can somewhat similar to a muffler if you look underneath your vehicle. But without fail, they will be the one nearest the engine. And what's inside of these is actually a ceramic cast element that has a special coating on it. And so the exhaust flow coming through here, this will actually be a honeycomb. If you look at it closely, all of them I've looked at closely, the air passages in them are hexagonal, and they're stacked just like a bee's honeycomb. And I'm doing a poor job of drawing this, but hopefully you get the idea. But this will be ceramic. This is your airflow. And the inside of these airflow passages are coated with a special material that helps complete the incomplete combustion. But I drew this giant size because in most of them, this air passage here will be about 1/8 of an inch wide. Well, if you're trying to shove your exhaust through a whole bunch of little 1/8-inch tubes, it actually does restrict the flow of our exhaust gases, but it does a lot of accidental muffling too. So our mufflers got smaller and a little bit different design when they're used with catalytic converters. Any thoughts or questions about those before I talk about one other thing? So back in the early 60s, there was an idea patented called exhaust gas recirculation. Hopefully I spelled that close to right. So the idea was that we've got this big cylinder and this big piston, but when we're just cruising down the road with 10% throttle, we don't need that whole cylinder full of air and fuel and making full power all the time. So exhaust gas recirculation was actually invented for the purpose of trying to increase fuel mileage. So the idea, when it was first conceived, was that this cylinder we're using, instead of filling the whole thing full of fresh air, that we got to try and balance with our fuel mixture, why, when we don't need all that power, what if we fill part of it full of an inert gas. Can anybody tell me what's the definition of inert? Nobody gonna help me out? Well, it's talking about something that does not react easily. In some cases, they'll say at all, but usually all these things they talk about as being inert, they will react if you get some extreme circumstances. But we're talking about, okay, the things we're reacting with are oxygen and fuel and that kind of a reaction. Well, what if we put something in here that does not easily react, and we filled up part of this space with it, and then we just use this for our reaction or our combustion? Well, if we could do that when we didn't need full power, and then we could take that away and use the whole thing when we did need full power, seems like a good idea. And in some of the engines that managed exhaust gas recirculation in that way, it kind of worked out okay. It wasn't a bad deal. Well, it's I don't know, the last 30 years or so, the exhaust gas recirculation has been managed differently as far as how much is used and when, and it's being used to reduce what's known as the quench area and reduce the oxides of nitrogen. The NO2 we talked about. So what quench area means, if we look at when our piston is all the way at the top, all of this surface of metal that's touching our combustion, it actually interferes with it somewhat. In that, okay, it seals off the oxygen from the one side of the fuel molecule that's right against that side, and it inhibits the flow of the flame travel, and it actually absorbs so much heat that it quenches or puts out the fire as if we have our combustion starting right here and it travels outwards, well, when that combustion reaction reaches the surface of this metal, it quenches or puts out the fire basically. And so all along this surface area, you'll actually have, that's where the majority of your undesired combustion happens, and your undesirable emissions from that occur. Well, if they can swirl, so the idea is that the exhaust that's coming out our tailpipe, it's mostly already inert because, okay, it's from nitrogen, which is inert, and a bunch of CO2, and the way it's recirculated, typically that's about all that's in there. So it's stuff that does not react, and if they can swirl it in there in such a way that this outer area here is that area is occupied by inert gas, and then just this area here in the middle is where we're having our reaction. Well, there's less of that quenched area, and therefore less of the oxides of nitrogen. So that's the way EGR is typically being managed by the engine control computers. In some engines, it is used more in a way to help with fuel mileage, which is at low throttle, but they seem to be far more concerned with putting a certain amount of it in under heavy throttle to reduce this oxides of nitrogen. So the way that's done, and I'm going to draw you a crude picture again. If this is our engine, and we're looking at the top of our engine. And this is gonna be our front. Say we've got our exhaust pipe coming out here and it's going back to our tailpipe. Well, right here somewhere, we're gonna take a little pipe, and this would be our fresh air coming in. We're gonna take a little pipe here, and we're gonna run around over here. And we're gonna put a valve here that we can turn on and off, and turn it partially on and off to control how much exhaust is going back in our intake. Now, most modern vehicles right in here somewhere, they will take and put a cooler, which typically what it will do is have a bunch of little bitty tubes for the exhaust to flow through, and then around those tubes will be a chamber that has antifreeze in it. And the idea is, okay, we're taking extremely hot exhaust, maybe it's 1400 degrees or something, and running it through this and knocking the edge off the temperature, trying to get it back under 1,000, and then dump it in here. Well, there again, pros and cons to everything, but the biggest con with this is we're dumping black soot exhaust, which contains a bunch of stuff like that, in where we really wanted that clean filtered air. So it adversely affects engine life, as you can imagine. The other problem we've seen frequently is what happens if we get a hole in one of them little tubes right there. We dump a bunch of antifreeze into this pipe. And what happens, so I'm going to draw our cylinder again. Ooh, that's really an ugly cylinder. That's even worse than usual. Let's try again. So when our piston comes up on our compression stroke, as we've been talking about all this time, by air we can compress it. Can you compress a liquid? You're right, Joe, you can't compress a liquid. So this space that's required on top of this piston, what happens if this space, we'll just pull some fun numbers out and say this is a quart. What if there winds up being 1.5 quarts of liquid on top of that piston? Well, what happens? What's that?
Probably gonna break a hole in the top.
You're right. Something's got to break. That's exactly right. So that piston comes up, and it's still trying to come up, but there's liquid here preventing it from coming up. Something's got to break. In some cases, it's the top of the piston. In most cases, what we're seeing is the cylinder head is substantially strong, that that's not what breaks. But in the vast majority of cases, what breaks is our connecting rod. The connecting rod will break, and when it breaks, a broken hunk of it flings out the side and breaks a hole in our engine block. Pretty undesirable result, huh? So that is one of the reasons why we see a lot of folks looking to, if they have vehicles that have this exhaust gas recirculation, and there again, I work primarily on diesel pickups, but in diesel pickups we see a lot of folks that are going this EGR cooler. They're either replacing it with an aftermarket one that has much thicker walls than the factory one, or just removing that system altogether. And fellas, I am not in favor of trashing our environment. I think we need to leave things for our kids better than we used to have them. But I think we're straining at gnats here. The infinitesimally small amount of advantage we get out of that system it's so small nobody's successfully even measured it. So if the result isn't measurable, but the potential damage to my family's checkbook is measurable, I can't blame the guys that are deleting it. I guess the only other, as far as emissions control that has commonly been used in any automotive application that I can think of is one called air injection. It was really popular late 80s, clear up through the late 90s. And we just don't see it anymore, and I'm honestly not sure exactly why. But there again, if down here in our exhaust we have our catalytic converter, and a lot of times you'll see in literature that abbreviated as CAT. Well, our incomplete combustion gases coming out here that we're trying to finish that reaction in the catalytic converter, in a lot of cases, that can be helped if we have a little more oxygen to work with to finish that reaction. So what was done on a lot of engines at that time is a lot of times they were belt driven off the engine. There'd be just a little air pump, and it would have a little pipe pushing air into the catalytic converter. The second common variant of that, instead of having a pump, was known as pulse air. And all they had here was a check valve, basically. They had fancy names for it. But are y'all familiar with what a check valve is? Can you tell me what a check valve is, Cole?
No.
Okay. How about, you want to tell them, Rich?
Yeah, it lets things go in, but won't let it come back.
Correct. So it lets things flow one direction, not the other direction. So they would have a check valve here that in essence was a seat and a ball type situation. So you can see this is actually connected somewhat indirectly to our exhaust. And we talked about how our exhaust is pulses, right? So when an exhaust valve on our engine opened and we got a pulse of exhaust, it would seat that ball and not let exhaust go out there. But there's actually in an exhaust pulse, there's a fraction of a second where in between those pulses you wind up with a little bit of vacuum. And they were using that little bit of vacuum to just pull some air in. So they would just have a little piece of foam on here to keep the dirt out of the check valve and a check valve, and let the natural pulses of the exhaust draw some air in. So that whole idea to introduce more oxygen into that catalytic converter was typically abbreviated as air or talked about as air injection. And the explanation I've gotten is that some of the catalytic converters now have a form of that pulse air injection made into this neck of them anymore, as well as the coating in there is different than what it was when that extra air was so important. And so you just don't see those on, Chucks, I haven't seen it on anything made in the last least 15 going on 20 years. But at the same time, if you've got that air pump and it's running off of a fan belt and it locks up and doesn't let the fan belt turn, it also turns some of your other important items on the engine, it becomes important that day. Just gonna take a quick look, make sure I well, I guess I did forget one, fellas. It won't take long, but this is something that is common in modern diesel engines. So after the catalytic converter, there is, in most of them, a device. I keep getting that one. I need to find the trash can. Pull that away. There's a device known as a DPF, is the way they abbreviate it. It's a diesel particulate filter. And it is right after the catalytic converter, and it is usually a gigantic can. The ones we typically see, they're 5 or 6 feet long, and they're a good foot in diameter. And they have a honeycomb in them, similar to the catalytic converter, but it's actually not a straight through air passage like the catalytic converters typically are, and it's designed to catch the soot. And soot, most often, if you look at it microscopically, it's a little semicircular shaped whisker of carbon that in some cases is oily carbon. You know, it's got some oil elements to it. And it's what in our diesels compromises a fair amount of when you get any black smoke out of the tailpipe. And if you're in areas where there are lots of people using lots of diesel engines, big cities, they say that that is one of the biggest contributors to the brown cloud, is the soot coming out of the tailpipe of diesel engines. So the idea is to catch that stuff and not let it just come out into the air. Well, you can imagine it can only catch it for so long, and then it's got to do something with it. And what they've wound up coming up with is they catch those whiskers and get them to kind of pack together, and then they superheat them, and it comes out as balls that then don't float in the air like the whiskers of soot do. They'll actually, you know, use gravity and go to the ground. Well, the way they're superheating them in most cases is with fuel. So as crazy as this sounds, what they're doing is they'll fire the injector while the exhaust valve is open. When you fire the injector with the exhaust valve open, where's that fuel go? Right down the exhaust pipe. This catalytic converter winds up being hot enough that it ignites it. And so then that flame traveling through the diesel particulate filter superheats those whiskers enough that they wind up, a bunch of them combining into a ball and getting blown out the tailpipe. So that's known as a purge, when they purge the diesel particulate filter. Now, in many cases, the later diesel particulate filters, they're doing 2/3 of their purges. In a lot of the management systems, they'll do 2 purges with urea, and then the 3rd purge will be with diesel fuel. So you've heard of diesel exhaust fluid or blue DEF. In most cases, that is derived from distilling hog urine, and it's actually a concentrate of urea, and they're using it, injecting it at certain times to clean the diesel particulate filter. Sounds pretty wild, huh? I saw your face go. I made the same face first time I heard it, probably the first 100 times I heard it. So that's kind of a quick snapshot of the different things that have been invented to try and keep our air clean. Some of them are more effective than others. But that's kind of a quick snapshot of emissions controls. Any questions on those? Any questions in general come to mind from what we discussed tonight?
Would you make the same recommendation on air filters as you did oil filters last week as far as brand?
Yeah, in general I would. You know, the cheaper Fran and Perlator and Mighty filters are cheaper because they're typically not as well made. And I guess what I tend to recommend is stick with the factory type stuff. It usually works best. One thing that comes to my mind is, okay, I work with a lot of Cummins engines. Cummins gives a list they recommend with their engines. Wicks, Baldwin, Donaldson, or Fleet Guard are the brands of filters they recommend. Interestingly enough, if a Cummins engine ever sees a Cummins dealer with an orange Fram oil filter on it, they void the warranty on the engine immediately. Does that tell you a little something about them orange cans?